The first story in today's show is brought to you by the confusing nature of Western languages, and the English language in particular. While perusing press releases and science articles, I came across the headline Mercury helps to detail Earth's most massive extinction event. Were this an episode of Xena Warrior Princess, I might have assumed the god Hermes had decided to use his other name and found a new way to be a trickster. This is not an episode of Xena, and I am more of an astronomer than a warrior anything. So when I read that headline, I thought, cool, they must have found something on the planet Mercury that tied into a mass extinction here on Earth. Yeah, I got excited that something so terrible must have happened to our world that Mercury was affected too. I'm not proud. I'm just apparently easily excited by mass extinctions. I was also very wrong. As we'll discuss in our first segment, that title, Mercury Helps Detail Earth's Most Massive Extinction Event, refers to the element mercury in rocks and how scientists used its presence in Earth's geologic record to finally figure out one prolonged event killed 80 to 90% of life on our planet. That beguiling could mean many things title came from a press officer paid to make people like me click through to read papers we might not otherwise read. To that University of Connecticut press officer, kudos. You did good. Today, we discuss one mass extinction, 3 stories with volcanoes, star formation, galaxy dissolution, and the ill-named dark energy and dark matter that make up the majority of the universe, and rockets. There are always rockets with aerospace correspondent Eric Mattis. We bring you all this and more right here on Escape Velocity Space News. I am your host, Dr. Pamela Gay, and I am here to put science in your brain. Last week, we took a really hard look at climate change, extinctions, and all the bad things that sometimes happen on our planet Earth. I've got to admit, I don't enjoy understanding climate science. And this week, we are not going to discuss climate science. We are going to start things off with a mass extinction. Because let's face it, sometimes mass extinctions can be pretty cool, especially when they have nothing to do with us or the life we live. About 252 million years ago, before the Neanderthals, before the large dinosaurs, back in the age of trilobites and sail-backed amphibians, something caused a great dying that came in 3 waves that together killed more than 80% of marine species and 70% of terrestrial vertebrates, as well as vast numbers of insects. This was, in fact, the largest known die-off of insects. Although the ancestors of the cockroach, which originated about 320 million years ago, they were able to survive. Because cockroaches. This great dying is scientifically called the latest Permian mass extinction, and it marks the line between the Permian and Triassic eras. This was a bad event, and different regions took anywhere from 3 to 10 million years to recover. Let that sink in. Earth was essentially dead for longer than humans have existed. Due to overlapping ages, the volcanic eruptions that formed the Siberian traps have long been identified as a possible cause of the extinction, stretching from the Ural Mountains in the west and ringed in by the southern and eastern Siberian mountains. This vast landmass of basaltic lava and tuff was in place during a series of events spread over hundreds of thousands of years. To prove that these eruptions caused the mass extinction, Researchers needed to show that the volcanoes of Siberia affected the entire world. This evidence, in the form of the element mercury, was identified in geologic samples from 4 new sites that would have been on the opposite side of the Earth from Siberia 250 million years ago. These samples have the same isotopic ratio as mercury from volcanoes, and they provide evidence of long-distance atmospheric transfer of mercury specifically from volcanoes. According to team member Tracy Frank, quote, "Knowing the age of these deposits, we can more definitively tie the timing of the extinction to the massive eruption in Siberia," end quote. What's more, by comparing different samples from what was on land and in the sea at the time of the eruptions, data analysis led by Jun Xian clearly shows that the extinction on land happened 200 to 600,000 years before the extinction in the ocean. Like the extinction we discussed last week, this was an ocean anoxic event, and the loss of oxygen in the water led to the loss of life in the water. While researching this story, I tried to find out if this kind of a massive volcanic eruption could happen again. Could 7 million square kilometers just get covered over by lava from a new mantle plume generating new volcanoes? From the geologists I heard from, the answer was it could happen, but it would happen slowly. So this isn't an us problem. This is a many, many generations away, if ever, kind of problem. While we may not need to worry about continent-coating volcanoes, we still have plenty of examples of eruptions that can disrupt entire regions through combinations of ashfall, lava, earthquakes, and tsunami. 1 year ago, on January 15th, 2022, the Honga Tonga Honga Haiapi volcano erupted, devastating the island nation of Tonga and generating a shockwave that would be detected wrapping around the world twice. In a new paper in Earth and Planetary Science Letters by Katora Terume and Kazunori Yoshizawa, a form of analysis called back projection was used to understand how seismic measurements correspond to eruption activity. Seismic waves are like waves on a pond that are created by thrown rocks, diving birds, and falling rain. For most lakes, there is a constant noise of things generating waves, but it is possible with enough data to work backwards and understand where the largest waves originated. Through their analysis, this team determined the eruption had 2 phases. Per the press release, the sequence of eruptions occurred in 2 main parts. The first sequence began at 0402 UTC on January 15, 2022, then escalated into major explosions at 0415 UTC and 200 to 300 seconds after. The entire sequence lasted at least until 0435 UTC. A second sequence of eruptions began about 4 hours later and continued from 6 to 7 minutes, including a massive eruption at 0831. Satellite imagery recorded the resulting dramatic ash cloud from the first eruption sequence, but until now the precise details of the underwater events have remained elusive. End quote. I know this is a bad analogy, but it reminds me of water glugging out of a bottle. Only here, it is lava that pulsed out every 270 seconds-ish. The reality is we're not entirely sure why it pulsed like this, but it is possible that it was due to the atmosphere creating a resonant oscillation with the Earth. More research is needed. The idea that our planet's atmosphere can cause volcanoes to pulse at 270 to 280 second intervals is kind of amazing, and simultaneously something I want us to see again to study more, and that I hope we never experience again in our lifetime. Geology, astronomy, these sciences are full of things actively trying to kill us. We really can't take it too personally, though. It's a star-eat planet rock smash rock universe out there. And sometimes these destructive forces can lead to truly beautiful results. Back in 2013, a group of researchers discovered that a small object in the outer solar system has a set of rings. This object is the 250-kilometer across icy object Chiriclo, which orbits at a distance between Saturn and Uranus. Until 2013, we hadn't thought such a small object could have rings. And the rings discovery was, in some ways, just a fluke of geometry. On that particular night, Chiriclo was predicted to pass between the Earth and a star. These kinds of alignments, called occultations, allow researchers to measure the width of asteroids and icy objects. Basically, the longer an object blocks a star's light, the bigger the object. In this case, however, they didn't just see the light from the star dip as Chiriclo passed in front of it. They saw additional pairs of dips that indicated there are ring systems orbiting 391 kilometers and 405 kilometers out. These rings appear linked to water ice detections and may be icy debris confined into rings by kilometer-across moons. To put the scale of this system in perspective, if we set Chiriclo on Texas, it would fit between Austin and Dallas with room to spare. And the rings would stretch 2/3 of the way to Oklahoma City to the north. This is a system smaller than many one-day road trips that we're able to see from Earth while it orbits beyond Saturn. And now the JWST has seen it too. Researchers calculated out that from its position beyond the moon's orbit, JWST could see Chiriclo pass in front of a star on October 18th, and special target of opportunity time was granted to observe this occultation. And they once again saw the dips in starlight that occur as the rings passed in front of the star. These observations are still being analyzed, but according to observer Pablo Santos Sanz, quote, "As we delve deeper into the data, we will explore whether we cleanly resolve the two rings. From the shapes of rings' occultation light curves, we also will explore the ring's thickness, the sizes and colors of the ring particles, and more. We hope to gain insight into why this small body even has rings at all and perhaps detect new fainter rings." End quote. This was the first time an occultation observation was attempted with JWST. And to me, one of the most impressive parts of this observation was they successfully calculated how from JWST's moving and movable perspective, they could point to catch Chiriclo's rings and only the rings passing in front of a distant star. This level of precision and accuracy is truly amazing. Chiriclo is currently classified as a centaur. One day, the gravitational pulls it experiences from the outer planets may send Chiriclo into the inner solar system, where it will take on the distinctive appearance of a comet. Our solar system's habit of periodically sending material from the outer solar system in towards our planet puts us in the curious position of being scientifically grateful we have meteorites to study, while we also hope nothing too big gets flung our way. The reality of it is, our world formed through the merger of myriad smaller objects that crashed together and stuck. By studying the compositions of meteorites, researchers pieced together where the original planet-forming disk, the materials that make up our planet, originated. I'm going to murder an analogy here. You've been warned. Imagine the kitchen counter of a messy baker. Splattered material on the counter might have come from the bowl of liquids, from the bowl of dry ingredients, or from the frosting bowl. If some CSI kitchen team analyzed the splatters in a mass spectrometer and then analyzed a cake, they'd be able to say what percentage of the cake is made from each kind of splattered ingredient set. in our solar system, we know different elements survived in different places when our sun first heated up. Fragile elements called volatiles were easily blown away and destroyed in the inner solar system, but they survived in the cold outer regions. Potassium and zinc are two of these elements, and in a pair of new studies led by Rasia Martins and Nicole Nye, researchers matched the different forms of zinc and potassium found in different kinds of meteorites to what we see on Earth. They find 10% of the Earth's mass came from objects that originated in our outer solar system, and 20% of its potassium and 50% of its zinc came from once distant objects. So I guess we can say we're somewhat salty due to the impacts of outer solar system materials. Science is weird, and it only gets weirder the further out we look. In the next segment, we're going to explore star formation and the merging nature of the galaxies they occupy. Stay tuned. As someone who lives online, I often stumble across the meme of Star Trek Voyager's Captain Janeway proclaiming, "There is coffee in that cloud," and wondering what could ever provoke her to say that. There are lots of things in the darkness of space, but my coffee-loving heart fears to say, coffee is absolutely not among them. Exactly what is within the dark molecular clouds that form star systems like our own was the topic of a recent JWST observing campaign. The observed dark cloud, Charmeleon 1, is about 630 light years away. To the JWST's infrared cameras, this cloud is semi-transparent and background stars appear as small orange dots. We also see the warm glow in the image's upper left from the protostar SED 110 IRS-4. While JWST's image is truly stunning and just might be my new screen background, the real information isn't in the image. It is instead in the spectra, in the lines of brightness and dark that appear when the light of the stars is spread out into a rainbow. This process is what is shown in Pink Floyd's Dark Side of the Moon album cover. That album was released March 1, 1973, and we'll be taking a closer look at the electromagnetic spectrum in our March 4th episode. JWST doesn't exactly use a prism, but the physics is the same, and in the bands astronomers can identify the chemical fingerprints of different atoms and molecules. And while JWST didn't exactly find coffee, it did find ethanol and acetone, and a variety of more complex organic molecules. So if you want to kick back with a drink and take off your nail polish, this cloud has you covered. Just no coffee. Those additional molecules, which take the form of ices, include ammonia, methane, methanol, water, carbon dioxide and monoxide, and other molecules that bring together carbon, hydrogen, and oxygen. This is the first time we've been able to get this kind of an inventory of the ices in giant molecular clouds. And it is a reminder that all the gases we now breathe were once just ices hanging out between the stars. What wasn't found were sulfur-containing molecules that were expected. According to team member Dana Chasm, quote, "The ices we observed only contain 1% of the sulfur we're expecting. 99% of that sulfur is locked up somewhere else, and we need to figure out where in order to understand how sulfur will eventually be incorporated into the planets that may host life." End quote. It is possible that instead of being in ices, sulfur is instead tied up in minerals, dust grains, and sulfur-rich atmospheres of worlds like Venus come not from ice, but from rock. Science is done in a lot of different ways, and astronomical discoveries often come from people looking very carefully at super weird or beautiful looking things and asking, how did that happen? And then going off and finding more of that thing that is either older or younger. For instance, to understand our solar system, we studied a dark molecular cloud. Where it gets tricky is when we don't know what the older or younger versions of an object might be. Consider the ultra diffuse galaxy. These weirdo systems take the stars of a normal, middling-sized galaxy and put them in a system with no gas for new star formation, and then mix in either too much or too little dark matter. We're going to take a closer look at dark matter in the next segment. Basically, it is stuff that doesn't interact with light, doesn't give off light, and isn't made of the kinds of particles we're made of. It does have mass, and it does interact through gravity. Most galaxies have more dark matter than luminous matter, and the ratios of mass to light are fairly consistent when researchers compare similar kinds of galaxies. Except with ultra-diffuse galaxies. Our only examples of galaxies with potentially no dark matter are ultra-diffuse galaxies. And our only examples of systems that are almost purely dark matter are also ultra-diffuse galaxies. To try and figure out how this happens, researchers used one of the largest telescopes on Earth to study one of the closest ultra-diffuse galaxies in the sky. In images from the Subaru telescope, researchers mapped out red giant stars in a galaxy cataloged as F8D1. Located in the M81 galaxy group, this system is about 12 million light-years away. In these extremely deep images, researchers were able to just make out faint streams of stars reaching away from the galaxy. These kinds of streams, called tidal tails, form when a galaxy interacts with another system and is disrupted. According to a new paper in Monthly Notices of the Royal Astronomical Society that was led by Rokas Zemaitis, researchers speculate F8D1 was disrupted during a recent close passage to M81, which would have stripped its gas and quenched its star formation. And they say, quote, "This leaves open the possibility that many other ultra-diffuse galaxies could be the result of similar processes, with the most telling signatures of this lurking below current detection limits." End quote. If this is true, what we're seeing are the scattered out remains of devastated systems. Consistently, they have had their gas removed, ending the possibility of new star formation. In some cases, the majority of the stars were stripped out as well, and in other cases, the majority of the dark matter was pulled away. Like a puffer fish bloated up in the face of danger, these systems spread out. But the gravity of their attacker did its damage, effectively killing these galaxies. Seeing if this kind of a story can be proven through the imaging of additional, more distant, ultra-diffuse galaxies won't be easy, but is certain to be on the task list for future many-meter telescopes. The story of our universe is not one of calm and gentle interactions. We talk about stars exploding, asteroids impacting, gas clouds collapsing, and galaxies colliding. At every scale, we see systems growing larger over time by gravitationally consuming the material around them. The largest of these cannibalistic interactions are galaxy cluster mergers. Systems of hundreds to thousands of galaxies have been gravitationally coming together since the beginning of the universe, and these systems will gravitationally pull one another together. Our own galaxy is part of the blandly named local group of galaxies, and our group is falling into the Virgo supercluster of galaxies. It is hard to get a picture of what cluster mergers look like from inside of one. So we look at other systems to see what we can see. Located 780 million light-years away, Abell 2256 is a system of 3 galaxy clusters undergoing a merger. In any one kind of light, this is a fairly unspectacular field, but by combining light from telescopes sensitive to everything from cool radio light to high energy X ray light, researchers could piece together a truly complex story. What we are seeing are galaxies of stars, shown in yellow and white, that are scattered throughout a vast blob of extremely hot gas that is shown in blue. This gas is heated through the collision and the immense gravity of the system. An unusually large number of the galaxies in Abell 2256 have central supermassive black holes that are actively feeding on infalling material. Jets from these feeding black holes appear as red tangles blasting through the system in radiolight. These galaxies may be undergoing a final wild burst of star formation as this collision shocks their gas into motion. And in the future, these may all be red dead systems without gas for additional star formation. All told, this single image combines X-rays from Chandra and XMM Newton in blue with radio data collected by the giant meter wave radio telescope, the low frequency array, and the Carl J. Jansky Very Large Array, all shown in red, plus optical and infrared data from pan-stars in white and pale yellow. The results of this work are described in 3 new research papers that NASA has shared along with this image. We'll link to all of this from our website, EVSN.tv. It will always amaze me how humans have learned how to observe our universe in so many ways beyond what we can see with our eyes in a visual light camera. We truly can't get a full understanding of what is going on without looking at every color in and outside the rainbow. The high energy part of the spectrum, the X-ray and gamma ray regions of light, are where we go to look for some of the wildest objects in the universe. In the last story of this segment, we have one of the wildest kinds of objects of all, a magnetar. These stellar remnants are a special form of a neutron star, which are the leftover cores of massive stars. Not all neutron stars are magnetars. Somehow, some neutron stars have developed massive magnetic fields about 1 trillion times stronger than the Earth's magnetic field. And just like the sun's magnetic field can periodically cause coronal mass ejections, neutron stars' magnetic fields can periodically cause massive outflows of energy. Case in point, magnetar SGR 1935 plus 2154 was spotted by the Swift telescope on April 27, 2020, when it gave off a burst of gamma rays. The same day, it also flashed in radiolight that was spotted by the CHIME radio array. A few months later, on October 5, 2020, this rapidly rotating object suddenly slowed down a bit. Sudden changes in speed have been seen before, but glitches have usually been accompanied by the star speeding up. A new paper with lead researcher Matthew Baring looks to explain how you slow down a magnetar. As he explains, quote, "In most glitches, the pulsation period gets shorter, meaning the star spins a bit faster than it had been. The textbook explanation is that over time, the outer magnetized layers of the star slow down, but the inner non-magnetized core does not. This leads to a buildup of stress at the boundary between these two regions, and a glitch signals a sudden transfer of rotational energy from the faster spinning core to the lower spinning crust." End quote. Explaining how a star could downshift requires an entirely different explanation. And the one Baring found is wild. He and his colleagues speculate that the magnetar gave off an eruption of particles that carried away angular momentum. As he explains, quote, "People have speculated that neutron stars could have the equivalent of volcanoes on their surface. Our findings suggest that could be the case, and that on this occasion the rupture was most likely at or near the star's magnetic pole." End quote. This event, in addition to slowing the star's rotation, also seems to have triggered a fast radio burst. While fast radio bursts, which are literally a short burst of radio light, have been seen from magnetars before, this is the first time one has been seen coincidentally with a backwards glitch slowing down the star. The kind of emission they believe occurred could also trigger radio emission, making for one nice theory to explain the entire complex picture. Before we check this off as solved, however, it would be good to see this happen more than once. For now, I'm just glad we have our small fleet of high-energy space telescopes and ground-based radio telescopes watching together for neutron stars to behave badly. Tying together everything we see into a nice, neat theoretical model isn't something that is generally easy to do. And as we'll discuss in the next segment, when left with a mystery, astronomers give it a terrible name and build more telescopes. Coming up next, we take a closer look at dark energy and dark matter, and how giant galaxies in the early universe seem to indicate we may know even less than we thought. Stay tuned. Today, we're going to take a closer look at the three major components of our universe and how they work together to shape space as we know it. Before I get into the science, I just want to acknowledge that astronomers are good at many things, but naming things is not one of them. The term Big Bang was coined by Fred Hoyle to mock colleagues. The rest of astronomy was like, cool name, let's keep it. And now what was meant to be an insulting turn of phrase is the name of the generally accepted theory for how our universe sprang into being. We are bad at naming things. In this segment, I'm going to be talking about two things: dark matter and dark energy. The first name comes from the realization that there is some kind of matter out there that doesn't interact with light. Dark matter is a perfectly on-the-nose name for this stuff. Dark energy, however, is the name we have given to whatever it is that is causing our universe to accelerate apart. When the name was coined, we didn't know if what we now call dark energy was a force, a pressure, an energy, or just some weird something no one had been creative enough to think up yet. Dark matter and dark energy are related insofar as they both define the shape and evolution of the universe. But the name dark energy is in no way actually descriptive. Let's just accept that astronomers shouldn't name things, but do name things, and move on. Okay, now for the science. One of the primary goals of science is to come up with a mathematical and physical explanation for everything we see in our universe. In a way, it all started with the planets. Early researchers struggled with geometry to find ways to mathematically model the planet's motions. Folks started from the assumption, false we would learn, that our skies must be more perfect than our world, and orbits were long assumed to be perfect circles, and sometimes circles on circles, and well, there was a lot of math involving circles. It was Johannes Kepler who finally broke down and tried matching the careful observations of Tycho Brahe to the imperfect ellipse, and found that if the circles got elongated just so, it would be possible to precisely match their past locations and predict their future motions. Kepler's three laws of planetary motion, published between 1609 and 1619, gave us the maths. The physics would have to wait until 1686 and Newton's laws of gravity. From mathematical models to physical understanding, we got there. It just took time. Today, as we look out across the universe, we can see with our telescopes a whole lot more than Kepler and Newton could ever imagine. Because light takes time to travel, we can see our universe as it was by looking at objects farther and farther away. We have the observational ability to look back in time. As we do, we see the modern structures of our universe melt away as we return to the once nearly smooth distribution of material that was formed in the Big Bang. As the story goes, once upon a time, nearly 14 billion years ago, our universe burst forth from a single point. All the mass and energy that is was confined to an expanding volume. It is hard to imagine what it was like. For the first fractions of a second, conditions were such that forces didn't work as we understand them. Something we can't explain that we named inflation caused the universe to balloon out with potentially every space the width of a hair expanding to span 10 million light years. It was so hot and so dense that nuclear reactions could occur as though the entire universe were a nuclear reactor. Protons came together, helium formed. There were a few overly eager atomic nuclei that went on to build bits of lithium and even traces of beryllium. And it was all over in less than 3 minutes. For nearly 400,000 years, this hot ionized gas expanded and cooled. Sound waves oscillated through the universe, creating areas with a little more and a little less matter. Light trying to fly free of the electrons and atomic nuclei was simply absorbed and re-emitted almost instantly, preventing any light from flying away to be observed. Then, in one short span of moments, that expanding universe reached a point where it was cool enough for electrons to bond with atomic nuclei. And when this happened, any light that was being emitted became free to fly outwards from every single point in space. Today, we see that light as the cosmic microwave background. The sound waves are reflected in its light, appearing as hotter and colder spots of different sizes. This light is the earliest thing we are able to see, and in this light, we can see no earlier. In explaining our universe, we have to match that cosmic microwave background in all its details. And the Big Bang Theory does this. We can match the distribution of those hot and cold spots, and we can precisely predict the average color that light should have. We have gaps in our understanding. Inflation is one of them. But with very few, and then something that did this happened here, black boxes, we understand what happened. And then we have a gap in what we can observe. The early universe was a cold, dark place. And it was only after the first stars formed that ultraviolet and higher energy light was able to start lighting up the sky and ionizing the cold gas to make it transparent to the light from those stars. Our observations are pretty rock solid back to about 1 billion years after the Big Bang. And in looking at those observations, we discovered we have some problems. First off, when we look at galaxies, including our own, we see them rotating. Except for a few ultra-diffuse galaxies, that is. We see them rotating at rates that can only be explained if the majority of the mass in the universe isn't the kind of mass that makes up us, televisions, chairs, and stars. This was discovered separately by Vera Rubin and Fritz Zwicky in the 1970s and 1930s from observations of our galaxy's rotation and of the motions of galaxies orbiting in massive clusters. Trying to measure the total mass of something we can't directly see has been a challenge. But we know that our universe's motion should put constraints on what is inside of that universe. When I was a student, we learned that if the universe had a sufficiently large density of mass and energy, it would one day collapse in on itself. But if it was sufficiently low, it could keep expanding forever. The easiest way to sort out which of these futures is real is to look back in time and measure how fast our universe was expanding and see what it is doing now. Our current expansion rate is called the Hubble constant. It has weird units. We look out at every 1 million parsec span of space, where a parsec is 3.26 light years, and then measure how many kilometers per second that span is expanding. Locally, we seem to be expanding about 73 kilometers per second per megaparsec. In 1998, researchers measuring the expansion rate of the universe at older and older times made the unexpected discovery that our universe is actually accelerating apart. While our maths had allowed this outcome, the physics we knew didn't expect it. And this is where a new something we called dark energy, was put in place to explain that acceleration. Mass is essentially just frozen energy. Energy can become mass, and mass can become energy. That's what Einstein's E equals mc squared really means. In looking at the ingredients list of our universe, we add up the mass and energy together. As we understand these things now, our universe is balanced out with 5% being regular matter like we're made of, 26% being dark matter that doesn't interact with light, and 69% being something we're going to call dark energy. Try as we might, dark matter hasn't been something we can detect in experiments. We see how it gravitationally affects light from distant galaxies, spins up our galaxy, and many other things. We see its effects, but we don't see it. It is most likely some kind of a particle, not too different from a neutrino, that has mass and isn't very interactive. It passes through us, is all around us, and just won't be seen except through gravity, which is the weakest force and not useful for detecting individual particles. There remains hope that we'll find a way to detect it. But for now, all I can tell you is dark matter is stuff. Stuff that is anti-interaction. And really, there are times when I get dark matter on a psychological level, even if its physics eludes us. Dark energy? It's a bit harder. We observe the universe expanding, accelerating apart. The energy needed to do what we see is roughly 1 proton of energy per cubic meter of space. As the universe expands, each new cubic meter still has that energy. It was originally thought that what's termed vacuum energy may be to blame. There is energy all around us, and it is constantly causing particles and antiparticles to pop into existence, where they self-destruct and pop back out again. From the maths, however, vacuum energy should be 10 to the 120 times larger than what we see with dark energy. And it isn't possible to explain a factor of 1 followed by 120 zeros as just a rounding error. And this, finally, gets me to a new paper that came out in the journal Physical Review Letters and was written by Alexandre Tkachenko and Dmitry Fedorov. I'm going to read the abstract of this paper to you because sometimes we need to acknowledge how specialized the language of science can get. Quote, quantum electrodynamic fields possess fluctuations corresponding to transient particle-antiparticle dipoles, which can be characterized by a non-vanishing polarizability density. Here we extend a recent proposed quantum scaling law to describe the volumetric and radial polarizability density of a quantum field, corresponding to electrons and positrons, and derive the Casimir self-interaction energy density and the field, the energy of the self-interaction energy, in terms of the fine structure constant. The proposed model obeys the cosmological equation of state, W equals -1, and the magnitude of the calculated energy, self-interaction energy, lies in between the two recent measurements of the cosmological constant lambda obtained by the Planck mission and the Hubble Space Telescope. To attempt to translate that, these two researchers have found physics that can explain how dark energy can be vacuum energy if its particles pop in and out of reality in a way that has polarization, an orientation that can be measured. They make predictions, and this is key. We can work to test if this theory is true. We can look for polarization and virtual particles from vacuum energy. And if this theory is true, they have found a way to use something we know exists, vacuum energy, to explain an effect we see, the accelerating expansion of the universe. By having just two authors on this paper, they are prepared to one day maybe get a Nobel Prize if this idea proves true. And I'm rooting for them. Their paper, which I have to admit has maths beyond my skills, it still makes sense. It's a description of what we see in our modern universe, and it fits what we see in the cosmic microwave background. Now, we just need to get better at seeing if we can fit what we're seeing in between the cosmic microwave background and the modern universe. We've started to discover that galaxies formed faster than we expected, and maybe differently from how we expected. We only have a handful of observations from JWST at the moment, but a new radio telescope array being constructed in South Africa named Hera hopes to detail out the distribution of cold hydrogen gas in the early universe. Between JWST and Hera, we may or may not find more observables to further complicate our understanding of the universe. I'm here for it. The next few years are going to be amazing. After the break, we'll be back to look at space missions new and ongoing, and aerospace correspondent Eric Mattis will be bringing us this week's launches. Stay tuned. Before we get to this week's rocket launches, I have an update on a mission we talked about last week, Lucy. This little spacecraft is working her way out to the Trojan asteroids near Jupiter. Along the way, she'll pass through the main asteroid belt, and where possible, researchers use this kind of an opportunity to get a good look at asteroids. Despite what we all learned in Star Wars, the actual asteroid belt is a pretty empty place, with one asteroid not being easily visible as more than a dot from any other asteroid. Seeing asteroids requires planning, and Lucy is now planning to visit one more asteroid than she was planning on visiting last week. According to Lucy collaborating scientist Raphael Marchal, who found the mission's new target, quote, "I selected 500,000 asteroids with well-defined orbits to see if Lucy might be traveling close enough to get a good look at any of them. Even from a distance, this asteroid really stood out. Without any modifications, Lucy's trajectory would take it within 40,000 miles of the asteroid, at least 3 times closer than the next closest asteroid." End quote. This asteroid is cataloged as 152830 1999 VD57. Currently, it doesn't have a name, but I suspect that will change in the not-too-distant future. Space is large. It is mostly empty. Everything is moving, and any kind of observation requires careful planning. With a few exceptions like the Moon, Earth, and Mars, we are lucky if we have just one mission at a planet at any one point. Sometimes, however, planning allows us to take advantage of luck. The Bepi-Colombo mission is on a slow journey to Mercury, and the Solar Orbiter mission is working to study the Sun from a variety of angles. Both these missions are primarily operated by the European Space Agency, and both are using the planet Venus to alter their orbits through gravity assists. Each pass of Venus brings us another chance to acquire science data, and researchers arranged the missions to pass Venus on August 9 and 10, 2021. The results of these observations have now been published in Nature Communications. As luck would have it, the sun was quiet during this approach. According to lead author Moa Pearson, quote, "These dual sets of observations are particularly valuable because the solar wind conditions experienced by Solar Orbiter were very stable. This meant that Bepi-Colombo had a perfect view of the different regions within the magnetosheath and magnetosphere, undisturbed by fluctuations from solar activity." End quote. Venus only has a weak magnetic field that is induced by the solar wind. This isn't ideal for a planet getting blasted by a nearby star. These observations, however, showed that even that induced field is enough to provide protection and help Venus retain its atmosphere. This implies that exoplanets without more Earth-like magnetic fields may still be able to retain their atmospheres. This gives us one more reason to think life just might be out there, somewhere among the stars. It may be just single-celled life, but hope. All these missions have one thing in common: a rocket put them into space. Joining me now would be aerospace correspondent Eric Mattis, but during our recording session, there was something that went horribly wrong with our connection. So he was able to get us all of the information, and I am now going to step in to bring you all of his amazing rocket news. And it's an all SpaceX all week kind of week with just 2 launches. A rideshare launch on January 31st and another batch of Starlinks on February 2nd. First, the Starlink 70 mission launched from Vandenberg Space Force Base in the morning of January 31st, carrying 49 Starlink satellites for the constellation and 4 rideshare payloads that are part of Italian company D-Orbit's Starfield mission in the Ion SCV-9 transfer vehicle carried atop the stack of Starlink satellites. Instead of the 15 minutes and done mission profile we've become accustomed to with Starlink launches, this one lasted almost an hour and featured one reignition of the rocket's second stage to put the Ion SCV-9 transfer vehicle where it needed to be and then send the Starlinks on their way too. Over the next 8 months, the Ion SCV-9, named Eclectic Elena after one of the company's employees, it will remain in space, providing power and telemetry to its 4 hosted payloads before performing an orbit-lowering burn and jettisoning its remaining propellant and battery chemistry to avoid becoming a hazardous piece of space debris. The company says it will burn up in the atmosphere in a few years' time. The 4 hosted payloads include a flight computer named Bunny, designed by a Swiss university student team called EFPL Space Team. The flight computer being tested on this mission will be used in a future pair of CubeSats the students are developing to study the Earth's atmosphere. Another payload on the Ion SCV-9 is a D-orbit sail made by German company HPS. They make a number of different sizes of D-orbit sails. This mission is using the smallest one, which expands from a 10 by 10 by 10 centimeter volume out to cover 5 square meters. The third payload is a bit unusual in that it's normally not a payload on its own, but rather has payloads attached to it. This is a separation mechanism. Separation mechanisms are essential for making sure satellites are released from the final stage of rockets that launch them, so it is critical they work. But because they are so important to the deployment of a satellite, no one really wants to be the first to trust their satellite to a new design or separation mechanism. Built by Ensign Bickford Aerospace and Defense, the NEA payload release ring is a new model of their company's separation mechanism. However, it's not actually going to be deploying an operational payload on this flight. Instead, the company is testing how the new design, this one being only 8 inches, 20 centimeters in diameter, performs. The final payload on the ION SCV-9 is very unusual. It's a small space-related box for a New Zealand company called Stardust Me. Stardust Me offers space burials, and inside the little box are several individually sealed 1-gram packages of human ashes. The box is going to remain on the transfer vehicle, and the ashes will be burned up when it re-enters the atmosphere in a couple of years. Booster 1071 completed its 7th flight into space and successfully landed on its drone ship, Of Course I Still Love You, in the Pacific Ocean to be refurbished for a future mission. Starlink 71, the other SpaceX launch this week, which took place at Kennedy Space Center on February 2nd, was much less complicated than the rideshare we just talked about. Booster 1069 completed its 4th flight and successfully landed on the drone ship, a short fall of gravitas in the Atlantic, after delivering the 2nd stage to space, where it deployed its 53 satellites into orbit 15 minutes after launch. And now, for some statistics for a few of the things that are in orbit around the Earth. There are 9 toilets in space. 4 on the International Space Station, 2 on the Tiangong Space Station, 1 soon to be burned up on the Soyuz MS-22, 1 on Crew Dragon Freedom, and 1 on Shenzhou 14. We keep track of orbital launches by launch site, also called spaceport. According to rocketlaunch.live, so far this year, the US has had 10 launches, China 5, Japan 1, and the United Kingdom has had 1. Of these 17 launches, there have been 2 failures, reminding us that space is hard. It is generally unsurprising that there are so few launches this time of year, but it was a really slow launch news week. But one great thing might have been missed in our show. So far, at the time of recording, SpaceX is preparing a massive Starship booster for static engine firing of its 33 engines. This is the last major hurdle it needs to complete in readiness for an orbital launch. It is possible this test will occur prior to this episode's airtime on Now Media. If SpaceX does complete its Starship booster test, we'll bring it to you next week. A version of SpaceX's Starship is being developed to return NASA astronauts to the surface of the moon at some point in this decade. More than 50 years will have passed between the last Apollo mission and that first Starship touchdown. And more than 56 years will have passed since the Soviet Union became the first nation to successfully land a spacecraft on another world. On February 3, 1966, the Luna 9 mission landed on the moon. Like the landings of many a Mars lander, the mission to the moon bounced a bit before coming to a stop. Once it did stop, it was able to unfold its landing pedal, deploy its cameras, and send back the first images ever taken from the surface of another world. The USSR didn't immediately release these images, but folks at the UK's Jodrell Bank Observatory, who were listening in on the craft, noted that the mission was using the radio fax encoding standard used by newspapers to transmit pictures. So, they borrowed a receiver from the Daily Express, and then the intercepted images were distributed globally. A BBC News article speculates Soviet engineers used this standard to, and I quote, ensure that they would get the higher quality pictures from Jodrell Bank without having the political embarrassment of asking for them, or to prevent the Soviet authorities from making political capital out of the achievement, end quote. Always trust the scientists to find a way to learn more and share more of what they discover. We're really bad at keeping secrets. That's it for now. We'll be back next week with more science and rocketry. Good night. Remember to look up.